All right, attempt 2 at this lecture, because I tried it a couple days ago, and my computer crashed 40 minutes into the lecture, and I lost everything, and I could not bring myself to do it again for at least another day. So I apologize for the delay in getting this lecture back out. All right, so what are we doing? We've talked about Newton's laws, particularly his first two laws, that the law of inertia, things that are in motion want to stay in motion, things that are at rest want to stay at rest, unless there are forces acting upon them. Forces cause changes in velocity, or accelerations. Newton's second law quantifies that in that the sum of the vector forces on an object results in an acceleration of that object, and how you relate the net force, or the sum of all the forces, to that acceleration is through the mass of the object. So let us continue on thinking about some of these forces and how to solve these sorts of problems. We spent a lot of time in the last lecture figuring out how you can actually calculate which forces are acting on the body. You have a force diagram. You figure out what are all the contact forces, what are all the things in contact with your system or your object that you're studying. They must therefore exert contact forces on your system or object. Then there is the one exception for this class, which is the long-range force of gravity, which does not need to be in contact with your object in order to exert a force. You do not have to be touching the Earth in order to feel Earth's gravitational pull. What I have here boxed is, again, Newton's second law. Newton's second law, again, to review, says all you have to do is add up all the forces, which they themselves are vectors, and that equals the mass of the object that have the forces acting upon it times the acceleration of that object. Contact forces could come in all shapes and sizes. And then we also looked at the example of the gravitational force, which is just the mass of the object times little g when you are near the surface of the Earth. This force is also sometimes called the weight, which is sometimes confusing. So mg is the weight of an object. All right, so my thought here is that I will just do a bunch of problems and use that to introduce new ideas along the way. So let's go back to the rocket. So there's a box that is attached to some sort of rocket exhaust pipe. And suppose the rocket, you are told the mass of this rocket is 10 to the 5 kilograms. And the rocket itself, the exhaust, exerts a force that is equal to about 5 million newtons. And the question is, what is the resulting acceleration of the rocket? And let's assume this is being done in space, far from anything that has any sort of gravitational tug. All right, first step is a force diagram. I draw the picture. I identify my system. I usually use a lighter color. And then I look for any object or whatnot that is touching my system which might exert a contact force. Really, I'm looking for anything in my drawing that touches this blue box that is not the system itself. You can see here that the rocket exhaust itself is touching the system, and it's, of course, that is where the force is being exerted, pushing the system to the right. And let's go ahead and identify right as positive and up as positive, even though this really is a one-dimensional problem. So that makes this force a plus 5 million newtons, because it's to the right. With your force diagram, you can then create a free body diagram, where I take my system and then I just represent it as a dot. and I look at all the forces that are acting on the object, and I draw them as arrows emerging from the object. So in this case, I would just draw one arrow, the force of the rocket, which is pointing to the right in this case. Newton's second law, mathematically, I always like to start super general and then get more specific as I go through the problem. So I might say in general, this must be true. Sum of the forces on the rocket equals the mass of the rocket times the acceleration of the rocket. I could even put little r's here. In this case, the left-hand side, there's only one force. So I'll write that as just force of the rocket equals mass rocket, a rocket. This really is a 1D problem. If you look at there's only one force and it's pointing in a particular direction. So you can think that this is really just a 1D problem of that's either, there's motion either to the left or to the right. So I could get rid of the subscripts if I wanted to. Now with this, I could then, I'm ultimately solving for the acceleration of the rocket, so I could rearrange. And in this case, I now know all the numbers. And I'll add a plus sign because the force is meant to be pointing to the right. Let's see. Kilogram is an MKS unit, so Newton's is kilogram times meters per second squared. This then gets you to 5 meters per second squared. And I'll be super explicit, it's a plus. It's a positive value. The acceleration is, since this is plus, it is to the right. The rocket accelerates to the right at about 50 meters per second squared, or if we think of little g as 9.8, round that up to 10, it's accelerating with about 5 g's of acceleration. Suppose I then say that the rocket thrusts for 100 seconds. I could ask, how much does the velocity change? So the rocket thrusts, it experiences an acceleration of 50 meters per second squared for 100 seconds. How does the velocity change? Well, in this case, we have solved for an acceleration, and the acceleration happens to be a constant. Therefore, the kinematic equations apply. So I can say that the final velocity in the horizontal direction is the initial plus the acceleration times t. Or that delta v is the acceleration of the rocket times t, which is 100 seconds. So then this is 50 times 10 to the 2 meters per second, or 5 times 10 to the 3 meters per second. Fairly substantial change in velocity, actually. The kinematic equation is applied because the acceleration we solved for ended up being a constant. Suppose then the rocket shuts off. What happens? In this case, I could go back and think again of what that free body diagram looks like. In this case, I have the rocket. That's it. The actual thrust has gone away. There are no forces acting on the rocket anymore. It would be incorrect to conclude then that the velocity is 0. Instead, sum of the forces equals mass of the rocket times the acceleration of the rocket. but there are no forces. The left-hand side is 0, equals the mass of the rocket, acceleration of the rocket. The acceleration is 0. Acceleration is how velocity changes. That implies the velocity then no longer changes. After the rocket turns off, it will continue to move at a constant velocity of whatever it was after it accelerated. If it had originally started at rest while the rocket was on, it would have went from 0 to 5,000 meters per second. Then once it turned off, it would just continue going at 5,000 meters per second indefinitely until there was another force in town that acted on the rocket. All right, that kind of gets to a previous exam question kind of related to this. Which of the following are true? The natural state of an object is at rest. Doubling the force exerted makes the object move at twice the speed. And essentially all forces operate through contact between two objects. The problem we just did relates to the first two. Particularly, it was an example that showed that the first two are wrong, and that the answer in this case is C. Essentially, all forces do operate via contact, with a few exceptions, the long-range forces. This problem shows that A and B are incorrect because we saw that when there are no forces, it's in some sort of natural state by itself, the object moves at a constant speed or velocity. Both, actually. And then in the case of doubling the force makes the object moves at twice the speed, that is making the mistake that forces connect directly to velocities. It's not F equals mv, it's F equals ma. Let us go back now. Let's actually prove Galileo's claim that objects near the surface of the Earth fall at the same rate with the same acceleration. So I always like to draw the Earth when it's involved, so I remember that gravity might be playing a role here. Suppose I have a hammer, and then I have a feather. I'm going to release them both from the same height and let them fall from rest. We could ask ourselves what forces are acting on, let's take the hammer first. And we are going to ignore air resistance for right now. So what I would do is I would identify my system, which is the hammer, and look for anything that is touching the hammer that might be a contact force. Since we are ignoring air resistance, you might think the air is touching the hammer. If we ignore air resistance, then there is nothing touching the hammer. There is no contact forces, but there is the gravitational force, which we have to always keep in mind. Then if I wanted to go to a free body diagram, I have my hammer, which I represent as a dot. And then there seems to be only one force acting on the hammer, the force due to gravity. And it's pointing downwards towards the Earth. I could be more specific here, and I could say Fg is, now I could make it positive mg, or I can make it negative mg. Depends on how I want my coordinate system to be. Maybe this time I will make down positive. So I'm assuming towards the Earth is in the positive direction. In which case then I would write the force due to gravity as plus mg, or toward ground. I could have also written it as, say, like plus mg multiplied by, say, j hat, if I wanted to use the ijk notation. I'm not going to bother with vectors because, again, if you look at this, you can see that it's, again, a one-dimensional problem. There's only forces in one dimension. Particularly, there's only one force in this dimension. All right. So then what's going on with the hammer? So again, start super general. Sum of the forces on the hammer equals the mass of the hammer times the acceleration the hammer experiences. There's one force, Fg, in this case. I guess this is hammer. I'll drop the arrows since this is 1D. Don't really worry about vectors. Then you can find that the acceleration that the hammer experiences is the mass of the hammer times little g divided by the mass of the hammer, or just simply g. The hammer accelerates at 9.8 meters per second squared towards the Earth. Notice how this acceleration does not depend on the mass. I don't need to know the number, the value for the hammer at all. Just to give some context, right? The mass of the hammer is about, 3/4 of a kilogram. The force due to gravity is therefore about 7.35 newtons. The acceleration is 9.8 meters per second squared for the hammer. I could do now the same thing with the feather. Let me skip right to the free body diagram. Again, there's only one force acting on the feather. That is the force due to gravity. In this case, it's m feather g. I guess up here I should have wrote m hammer g. And again, for the feather, the sum of the forces on the feather equals the mass of the feather, acceleration of the feather. And you again get the same exact expression, except there's the mass of the feather in the equations, but it cancels out anyway. And again, you get that the acceleration of the feather is just g, positive g particularly. It's g towards the ground. Let's look at that. So you got m feather. A feather is something like 10 to the minus 2 grams in comparison, which means the force of gravity on the feather is something like 10 to the minus 3 newtons. Yet the acceleration is still 9.8 meters per second squared. So even though they have very different masses, and as a result experience very different gravitational forces, I guess it's 4 orders of magnitude, really, between the force of gravity on the hammer and the force of gravity on the feather. So the Earth is pulling by very different amounts on both the feather and the hammer, yet they both fall at the exact same rate, or rather accelerate towards the ground at the exact same rate. So that if they were both released from rest, they would both have the same velocities as they travel towards the ground. And the reason this comes about is because the force of gravity depends on the mass, but so does the overall acceleration. Newton's law says that forces equals the mass of the object times the acceleration. And since both the force and the right-hand side of Newton's law has a mass in it, those masses cancel out. And as a result, the acceleration you get is independent of the mass of the hammer and the feather. So that was the idea when we looked at videos like this of seeing astronauts drop hammers and feathers on the moon, that they were able to do so, and both of them were able to hit the ground at the same time. In this case, with the moon, they were not accelerating towards the ground at 9.8 meters per second squared. They were accelerating towards the ground at something that's about 16% that. Because the moon itself, its gravitational pull is much weaker than the Earth. But nonetheless, so then, Newton's law would not have used little g, maybe it would have used like g sub moon or something like that with a little moon subscript or something, where it's the acceleration due to gravity near the surface of the moon. But nonetheless, it would have been the same for the hammer and the feather as we saw in that video. And as it would be the case on Earth, but they would accelerate at 9.8 meters per second squared. So then I could ask something like this. On Earth, you observe a feather falling to the ground at a constant speed. How many forces must be acting on the object? So in this case, I must conclude that the answer is C, more than one. It can't be none, because we know you're near the Earth, so there's gravity. It can't just be gravity, else it would be accelerating. So there must be something that is balancing gravity such that the acceleration is 0, which allows the feather to move at a constant speed. We could go back to the written work. If this is the feather, right, and it's experiencing gravity pointing downward, there must be some force, maybe it's the air or something like that, that is pushing back up on the feather. Because the only way you can get v is a constant only if the acceleration is 0. Remember, how velocity changes is just acceleration. But the sum of the forces equals the mass of the feather times the acceleration of the feather. If that is to be 0, that means that this sum must be equal to 0, which only can happen if there's at least 2 forces. I can't just have gravity and have it equal to 0, because that would imply that there's no gravity. So in this case, the air and the ground and gravity in this case must be balancing each other in some way. Let's look at a few other examples when there are multiple forces. I believe we saw this in the previous lecture. Let's go back to the person sitting on the chair. But now their legs are off the ground, and they're just sitting on the chair. And they're sitting at rest. And I could ask, is the chair exerting a force? And what is its magnitude, if so? I could also ask about the direction. I could just ask about what is the, if there is a force, it will be a vector, because forces are vectors. So I could just ask what is the magnitude and direction of this chair force. All right, so again, what do? Force body diagram, start by identifying your system. Oh, and I guess let's assume this person has some mass m. So I start by drawing my system. And I look for anything that's in contact with my system. In this case, it looks like the chair is connecting with the rear end of the individual. So there's a contact force from the chair. So I might expect some force of chair, which is occurring at the point of contact. And then we're near the Earth, so I also assume that there is some gravitational force as well. Okay. Let's draw a free body diagram. So here I am, the person sitting on the chair. I'm going to define up as positive in this coordinate system. So in this case, I would assume I would identify that there's gravity pointing downward. And I might make an estimate or educated guess that the chair is pointing upward in this case. Gravity is trying to pull me down, but I'm clearly not going down to the ground, so I might imagine that there's something balancing me off. Suppose you guessed incorrectly. Suppose you thought that the chair also pointed downward. As long as you're careful with your coordinate system and your math, actually the math will fix it for you. You'll just end up getting an answer that has the opposite sign as what you expected, which just shows you drew the vector in the wrong direction. All right, so if I had to think, next things I like to do is I like to write down what every vector is and assign it either a plus or a minus sign based on its coordinate, based on the coordinate system. So the force due to gravity I will write as negative mg. Negative because I'm defining down as negative this time. And then I'm going to, then I'm going to define F chair, the vector. I'm going to assume it's positive, and I'm just going to say it's, F. At some value I don't know. But maybe we could figure it out. Where it's probably assumed in this case that I know M and I know G. But I'm giving a minus sign and a plus sign specifically here to tell myself which direction these forces are pointing in. All right. Start super general. The sum of the forces on me is equal to my mass times the resulting acceleration I feel. The resulting acceleration I feel is 0, since it says I remain at rest and still. My velocity is 0, but more importantly, my velocity is not changing. So I therefore cannot be accelerating while I sit still in a chair. All right, so I'll get rid of the vectors since this is just 1D. Sum of the forces equals 0. So then I will write the sum of the forces. Sum means add them up. So I'll write force of gravity plus force of chair equals 0. In this first step, I'm writing the sum of the forces, and I have yet to include any information with regard to the coordinate system here. Here, Newton's law just says add up the forces. So in this case, I'm adding up the forces. Always have plus signs in this case. So no use of coordinate system yet. Here is where I might suggest doing some algebraic manipulation if necessary. Then when you're ready to plug in numbers or plug in values, that is when you introduce the negative signs. So at this next step, I would say negative mg plus f equals 0. So here, negative plus for the coordinate systems. Then just solving algebraically, we get that f is, and I'll be explicit, we get plus mg, which implies the force from the chair equals plus mg. The chair is pushing up on me, and it's pushing up on me with a force equal to my weight in this case, mg. Which, if you think about it, kind of makes sense, because I have the gravitational force, is pulling my weight down, or pulling me down, with a value equal to my weight, mg. So if the acceleration is going to overall be 0, that must be canceled out in the positive vertical direction. So the chair is then exerting plus mg pointing upwards, so that the sum equals 0. Consider a box that rests on the ground. And I attach a rope to the box and I'm pulling on the box with some force that I'm exerting through the rope. So you're pulling on box via rope. Let's assume the rope is at a 45-degree angle with the horizontal. And let's make it not. Let's make it 30, my favorite. And the rope has a force of 10 newtons. And it points along the rope. If the box is 5 kilograms, what is the horizontal acceleration? Alrighty. So here's a case of a 2D problem, but the problem really is only asking us to find the horizontal component. So force diagram, I'm trying to study the motion of the box. So I will define my system as the box. Then I look for what's in contact with the box. The ground is in contact with the box. The rope is in contact with the box. And then there's gravity, of course, pulling things downward. All right. Let's define up and right as positive. My free body diagram, there's the rope, which is at some angle. So I might draw it like this. There is gravity, which is pulling the box down. Then there's also the ground that it is in contact with. And if I think of this like the chair example, I might think that the ground exerts a force, maybe that points upward. We'll call it force of the floor. So I could write down what I know. I know the force of the rope is 10 newtons a long rope. So I could think, can I do any better? Ideally, I could write these as vectors. But we're told that the rope makes a 45-degree angle with the horizontal. So that angle must therefore be, 30 degrees, makes an angle of 30 degrees with the horizontal. So there is therefore a y component and an x component for the force from the rope. So in that case, it's 10 newtons times cosine, which is square root of 3 over 2. So the 2 divides into the 10. And then sine of 30 is a half. This is just 5 newtons. And I'll be explicit in that I'll have little plus signs in front of both, because I know by the direction of the force, it is pointing both in the positive direction vertically and the positive direction horizontally. The force due to gravity, I might write that as 0, comma, mg, minus mg, if down is negative. And then I have the force from the floor, which I actually don't know anything about, other than I have a hunch that it's probably going to be purely vertical. We'll get into that in a second. So I might say that the force from the floor is some value f, and I'll put a plus sign in front of it to, again, remind myself that I'm thinking that it points straight up. And up is positive. Okay. Now in this case, it's only asking about the horizontal component, though we could actually figure out the vertical and the horizontal component. And we will come back to that. But right now, let's just focus on the horizontal. So this first line is completely general. It says, using vectors, the vector sum of forces equals the mass times the vector resulting acceleration. Going back to the idea that you can treat each dimension independently, think about what's going on in the horizontal, think about what's going on in the vertical. We could break this up, if I wanted to, I could write this as 2 different problems. I could do one problem over here, where I could say the sum of the forces in the x direction equals the mass times the acceleration in the x direction. And then I could look at the y components of the vectors and say that in the vertical direction, the sum of the forces in the y direction equals the mass times the resulting vertical, or y, acceleration. Again, I can look at all the x, what's going on horizontally, by itself. I can look at the vertical part by itself. Since this problem is only asking about horizontal, let's just look at the left one. So in this case, I can look at my 3 vectors for the rope, gravity, and the floor. And this sum, again, is saying it's the x component of gravity plus the x component of the floor plus the x component of the rope equals the mass of the box times the acceleration in the x direction. Again, sum of the forces, there are 3 forces. I have 3 values in the sum. However, this one and this one are 0. If I just look at, where's my highlighter? The fact that the x components are 0 for these 2 forces makes this and this identically 0. So in that case, this just becomes the positive, let's see, what did we say? In the x direction, it was plus 5 root 3 equals mass times acceleration. We said the box was 5 kilograms, so then the acceleration in the x direction becomes square root of 3 meters per second squared. And again, plus. We solved for this and it was a positive number. The math tells us the acceleration must be to the right, which is likely not that surprising. You're pulling the box to the right, the box is going to then accelerate towards the right. So again, the same idea as what we saw with projectiles is that you can break the dimensions up and look at each one of them individually to get your answer. So So when I talk about the net vector force, the net sum in its two-dimensional vectors, and you'll see this in the homework, you essentially can just add up all the x components and then add up all the y components, and that answer overall is the net force as a vector. Let's look now. Let's go back to this contact force with the ground. Suppose you're in an elevator and it's moving down at a constant speed. What forces act on you? And then what are their magnitudes and directions? So I suppose it's moving downward at some constant speed. I'll put a little 0 to mean it's constant. All right, first things first, a force diagram. I'm studying my motion. So my system might be me. Then I see, is there anything in contact with me? I'm in contact with the floor. So F floor. And then gravity, of course, is still doing its thing. A free body diagram, of course, has gravity pulling me down. And then I'm in contact with the floor. And we could think again, why does it make sense that the contact with the floor would be straight up? Well, we know that you are moving at a constant speed. You know you are not accelerating. So it makes sense that if you're not accelerating, the net force on you better be 0. That is how you get 0 acceleration. So it makes sense that the floor will likely be pointing up and away from the floor. Let me define up as positive. This is, again, looks like a 1D problem. The force due to gravity then is negative mg. The force due to the floor, I don't know what it is, but I'll just say it's plus, F. Plus again, because I think it's going to point upward. Some of the forces on you. Oh, before I get to that. Maybe you thought, well, the elevator is moving and there's that big cable that he drew and that's what's causing the elevator to move, is that cable exerting a force on you. You gotta be careful. Because the cable is not in contact with you, so the cable cannot exert a force directly on you. Yes, it's exerting a force most likely on the elevator itself. But you are not touching the cable. You are only touching the floor of the elevator. So it's only the floor of the elevator that can exert a force on you, besides gravity. If that's not clear, rewind and think about that again. Forces require a point of contact. That was 2 lectures ago. All right, so the sum of the forces on me equals my mass times my acceleration. I have the force of gravity acting on me, and then I have the force of the floor acting on me. And that equals my mass times my acceleration, the latter which we've argued is 0. Again, notice here I've just added up both the forces. Sum of the forces, I added up a vector sum, all plus signs. Now I introduce in the next step, I introduce negative signs if it corresponds to the negative direction of my coordinate system. So now I might write negative mg plus F equals 0. Or again, that the force from the floor equals plus mg. The force from the floor is balancing the acceleration due to gravity's downward pull. So the force from the floor responds with an equal and opposite force in that case. These contact forces, which again really is all forces, besides the few long-range ones. Sometimes these contact forces between surfaces has its own special name. So these contact forces with surfaces are sometimes called normal forces. And you might think as opposed to anormal forces, abnormal forces, peculiar forces. No, normal is just a fancy mathematical word for perpendicular. So normal is just a way to say perpendicular. In that this is a force that points perpendicular to the surface. Which we saw in the case of the chair. There was a contact, you were in contact with the surface of the chair, and there was a force that was pointing perpendicular to the surface of the chair. It was pointing straight up, while the chair itself was horizontal. Standing on this elevator, you're in contact with the ground of the elevator. There's a contact force from the elevator pointing straight up, perpendicular away from the surface. I will admit I hate the fact that they're called normal forces, particularly in a physics 1 setting. Because I think the misconception here is that you think that the normal force is this one particular thing that is the same for every single problem. Whether it's, a chair or an elevator or a box on an incline. I could draw a ramp and there could be a box right here. The box is in contact with the surface of the ramp, and as a result, there is a normal force, sometimes given, I think your book uses capital N, but really it's just a contact force with the ramp. And in this case, it's again pointing perpendicular from the surface, but kind of at an angle. It's not always straight up, for example. If I were to push a book up against the wall, maybe I push the book up against the wall and I ask, what is the motion of the book? There are two things in contact with the book. There's the force from my hand, and then there's also a force from the wall. It's touching the wall. That contact force with the wall might be called the normal force being exerted by the wall. Again, really it's nothing but just the contact force from a surface. Its value always depends on the problem. It's not, another misconception. The normal force is not always equal to m times g. It's not the same thing as weight. The examples we saw above did happen to have it be the same as the weight. In this case right here, we saw that the contact force with the floor was mg. For the chair, we saw that the contact force with the chair did happen to be mg. But that is not always true. In a high school physics course, it often is the case that they're always equal. The normal force always happens to be the same thing as your weight. But that is not a general truth For example, going back to the example here where I'm pushing the book up against the wall. I'm moving in the horizontal direction, which has nothing to do with gravity. So it doesn't make sense that it should depend on at all with little g. Because what if I'm really pushing the book against the wall compared to just gently holding the book up against the wall? The wall has to respond in different ways. And neither of them have anything to do with gravity. So the normal force is not always mg. Do not think that it has to be. It really is just a contact force with a surface. Here's perhaps where confusion arises. The normal force is, however, equal to the, or rather, I guess, the normal force magnitude is equal to the value that would be read off a bathroom scale, or read off a scale. So sometimes it might be referred to as, and sometimes I do this too, or calling it the scale force. What that means is, you could ask yourselves, when you stand on a bathroom scale, what is the bathroom scale reading? You might think it's reading my weight. But remember, in physics, weight means something very specific. Weight is your mass times little g. So in the case of a bathroom scale, you're standing on a bathroom scale. Since you're standing still, there are two forces acting on you in this case, the scale itself and gravity. So you have a weight that's pulling you down, but then you have the bathroom scale that must be balancing that weight. The sum of the forces on you must equal your mass times your acceleration. If you're remaining still on the bathroom scale, your acceleration is 0. This sum of the forces must therefore be your weight plus the force of the scale pushing up on you. And if we define down as negative, it might be something like negative mg plus F scale equals 0. Or that the force that the scale has to push back on you is equal to, indeed, mg. The scale does have to push back with a force equal to your weight. And that is what the scale reads. The scale is essentially just a big spring, and when you step on the spring, it compresses. And the amount that the spring compresses, of course, causes a force that pushes you back up. You can experience that just by squeezing a string or a spring. And essentially what your bathroom scale is doing is it's calibrated so that for a given amount of compression, it translates that into a number. That number is, in that case, in the case of a horizontal scale where you're not moving on the scale, it is indeed your weight. Hence why we say a bathroom scale reads your weight. The force being measured by the bathroom scale, in that case, is equal to mg. So the little reading then reads off mg. However, we can think about this problem, and you can do this experiment at home to hopefully help you convince yourself that the bathroom scale doesn't have to read your weight. Only in the case where it's just you, the scale, and gravity does it read your weight, and everything is horizontal. Think of this case, and you could do this. Grab a family member or a friend. Stand on the scale and remain stationary, remain still. But while you are on the scale, have your friend or family member push down on your shoulders. Again, so that you're ultimately remaining perfectly still, but your friend or family member is pushing down on your shoulders while you're standing on the bathroom scale perfectly still. what does the bathroom scale read then? So again, your system is you. You're in contact with the scale. You're in contact with the hand that's pushing down on you. And then there's, of course, gravity. If I define up as positive, there's a free body diagram here where I might imagine that gravity is pushing down. The hand is pushing down. And then the scale is resisting and pointing back up. Again, why do you think it's resisting? If you're not moving, or rather you're staying still, your acceleration must be 0. So I would imagine that there has to be some balance of forces here. Else I won't, if I don't add up the forces and get 0, that's weird. Right, so I'll say force of the scale might be plus F, or I'll use the book notation. I'll say it's plus N. The force due to gravity is minus mg. And the force from the hand, I don't know how hard your friend is pushing you, but I know they're pushing you down, so I'll write this as negative F hand, say. So now there are 3 forces acting on you. So then, what does Newton's law say then? Sum of the forces equals your mass times your acceleration, which, again, if you're remaining still, is just 0. This is an example of equilibrium or static equilibrium. Well, I guess let's be careful. Static, I think, assumes your velocity is 0 as well. But this would be an example of force equilibrium. The forces are in balance. The sum of the forces, so we have 3 forces. We have the scale, gravity, and the hand equals 0. Again, sum of the forces, adding them all up with plus signs. Now I will introduce the coordinate system, which might introduce some minus signs for some of these. So this was plus n minus mg minus f hand equals 0. Or that the normal force, or the scale force, or what your bathroom scale reads, notice it's not mg, but it's mg plus f hand. Which, if you do this experiment, hopefully you'll notice, if someone pushes down on your shoulders, the bathroom scale reading increases. Obviously, your weight has not changed, your mass has not changed, the gravitational pull on your body has not changed. It's simply now the fact that the bathroom scale has to resist not only gravity, your weight, but also has to resist the fact that there are 2 hands that are also trying to push you through the scale into the ground. So the bathroom scale responds with a larger normal force, or a larger contact force, and that is what the bathroom scale reads. It becomes a larger number. And I'll let you try the same idea, but now imagine that you stand on a bathroom scale, but someone comes up from behind you and tries to lift you up slightly. Maybe they put their arms under your arms and gently try to lift you up. But you still remain in contact with the bathroom scale. You will notice that the reading on the scale decreases in that case. The bathroom scale does not have to work as hard to balance out all the forces. The bathroom scale therefore reads a smaller number. Yeah, so I had some examples again. So we're going to see the normal force a lot, and a lot of misconceptions around them. So let me recap again here. All of these are wrong. The normal force does not always point in the vertical direction. In these examples, it did. But in the case of me pushing a book against the wall, the normal force, or the contact force from the surface of the wall, points away from the wall. That might be horizontal. If it's on an inclined plane, like the ramp, the normal force points at an angle. The normal force is not always equal to your weight, mg. Hopefully this bathroom scale example conveyed that idea. do not just plug in mg. It is not always equal to mg. And again, thinking back to the book pressed against the wall, that has nothing to do with gravity. So g shouldn't appear at all. And then a misconception we'll see more of, that the normal force plays no role in your motion. It plays a very significant role. In the case of the bathroom scale, that was the force that stopped you from sinking into the ground. Something had to stop you from accelerating downward, because that's what gravity wants you to do. Something had to balance that out. The normal force played a very important role then. It kept you staying still rather than sinking. Here's some examples of all of these are true. The normal force does point perpendicular to the contact surface, which could be vertical, could be horizontal, could be at an angle. The normal force can be thought of as the scale force, i.e. is the value a bathroom scale would read. You could also do this experiment with a horizontal bathroom scale. Pick up your bathroom scale, assuming it's one of those small light ones, and press it against the wall. You can press the bathroom scale against the wall and it will read a number. The harder you press it against the wall, the larger that number is. Obviously that has nothing to do with gravity, because you're just pressing the bathroom scale against the wall. It only depends on how hard you're pressing it against the wall. It has nothing to do with your weight. So again, what that bathroom scale value is telling you, it's telling you how much of a normal force the wall or the surface is responding with. And perhaps that's where normal forces can get confusing, because it's very rarely ever going to be the case that I tell you the normal force is 3 newtons or something like that. Very often it's the case that the normal force can have a range of values that depend, and whatever it happens to be depends on what else is going on in the problem. Am I pressing the bathroom scale against the wall? Is 2 people pressing the bathroom scale against the wall? In both those cases, the normal force is different. And then we'll see, we'll probably see, that the normal force, if you ever are solving a problem, this one is a little bit more advanced, we won't see this for a while, but for the normal force, if you ever are solving a problem of Newton's laws and you get the normal force and it's a negative value, or rather it's pointing not away from the wall, but it might be pointing into the wall, or the normal force is pointing into the ground rather than away from the ground, or it's 0, that means that something's wrong. And what that likely means, as long as you did the math correct, is that means that you have likely lost contact with the surface. For example, I'm on a bathroom scale. Someone is lifting me up from underneath my arms. The bathroom scale number gets smaller and smaller and smaller. Eventually, the person might lift me completely off the ground. Obviously, in that case, I'm no longer touching the bathroom scale, so it reads 0. That is saying that the normal force has gone to 0. And you are either right at the precipice of losing contact or have lost contact with the surface. Alrighty. Very good. Let's see. This is what I want to do. That I did. We did some boxes. We did some 2D motion example, which you'll need for the homework. I guess I could quickly go back to this problem. We could now, just for completeness, solve. I guess it helps if you can see it. We could now go back to the problem of you pulling the box at an angle. We can now actually go back and figure out what's going on in the y direction as well. We could have done this before, but now that we have a better sense of what forces, what we might call them, there's this contact force with the floor. Maybe you want to call it a normal force. Again, I prefer to just think of them as contact forces with surfaces. We solve for what's going on in the x direction. We can now ask what is going on in the vertical direction. So the sum of the forces, again, there's the y component from gravity, the y component from the floor, and the y component from the rope equals the mass of the box times the acceleration of the box in the y direction. And usually when you're dealing with normal forces and surfaces, usually there's an assumption being made that you are not leaving the surface. So it's assumed here that the box is not floating into the air or sinking into the ground while you pull it in the horizontal direction. So in that case, you can set the acceleration in the y direction equal to 0. If it were non-zero, that would mean the box would start to float or that the box would start to sink. And since it's staying in contact with the floor, even though you might be pulling it across the floor, since it's not leaving the floor, that means its vertical motion in this case must be 0. Or that it's not accelerating off the floor or into the floor. All right, I wrote all these forces with plus signs. I haven't introduced a coordinate system yet. Now let me bring in the coordinate system. I have minus mg for gravity. I have plus f for the floor, using the symbol I defined up here. And then I have the y component from the rope, which we said was plus 5 newtons, equals 0. So essentially what we're solving for here, I know m, I know g, I know 5. In order to make sure that the box does not leave the floor, what this is telling us is that the floor itself must be exerting a force equal to plus mg minus 5 newtons, which in this case is positive. Why is it positive? The box was 5 kilograms. Oh, is this? No, it's not. Okay, never mind. Right, the box was 5 kilograms, so m is 5, g is 9.8. 5 times 9.8, whatever it is, it's greater than 5. So the overall value of this is positive. You know, if I say g is 10, if I round up to 10, then this is approximately 45 newtons. Plus 45 newtons. So again, what is that saying? It's a plus. That means the floor is pushing up on the box to keep it from sinking into the ground via gravity. And since it is indeed, this contact force is positive and pointing away from the surface, all of this is self-consistent. The box does not float into the air or sink into the ground. If you were pulling the box with a bathroom scale slipped underneath it while you were pulling the box, this is the value that the bathroom scale would read. It would read 45 newtons, which notice is not its weight. The weight of the box is the mass times g, little g. It's this first term. This is the weight. But notice what is being read is something that is slightly less than the weight. And again, why is that? You're pulling slightly upward with the rope, so you could think that there's a slight little bit of pull that you're doing to try to lift the box up and down, or in this case, up, rather.